This lesson is on air masses, fronts, and cloud formation. From this lesson, you need to be able to explain what happens to the density of an air mass when it gets warmer, what happens to the density of an air mass when it gets cooler, when an air mass will rise or sink, whether a cool or a warm air mass can hold more moisture, and what happens to the relative humidity and absolute humidity of an air mass as it cools. Some of these you can probably explain right now because they've been included in previous lessons, but a couple of these are going to be new today. All right, an air mass is a large body of air that takes on the characteristics of the area over which it forms. The main types are continental tropical, maritime tropical, continental polar, maritime polar, and Arctic. So fortunately, these names of these types of air masses pretty much explain on their own where these air masses originate and over what kind of area they originate. So here we have continental Arctic. So this is an air mass that forms over continents that are close to the poles. So you're going to get a bitterly cold and dry air mass from this. And just to go ahead and explain something very important, a warm air mass is always going to be able to hold more moisture than a similarly sized cold air mass, because a warm air mass, it's less dense, there's more room in there between the molecules for water vapor to exist. But a cold air mass, it's more compact and dense, and it doesn't have as much room for moisture to exist within the air mass. All right, continental polar. All right, so this is air masses originating closer to the poles that form over continents. These are also going to be cold and dry. All right, then we have maritime polar. Those are going to be your cool, moist air masses. Then we have our warmer air masses down here. We have maritime tropic. These are warm, moist ones that originate near the equator. Continental tropic. These are air masses that are hot and dry. They originate closer to the equator, but they are originate over land, which makes them more dry. So another kind of general rule is if an air mass forms closer to the poles, it's more likely to be cold. If it forms closer to the equator, it's going to be warm generally. And then your maritime air masses, the ones that form over water, they're going to be moist. The ones that form over land, your continental ones, they tend to be dry. All right, air density and pressure. If the temperature of an air mass increases, then its density decreases because that air mass has expanded. We've definitely talked about this before. If the temperature of an air mass decreases, if it gets colder, then its density increases because the air mass has contracted. Again, we've talked about that. So cool, dense air sinks, while warm, less dense air rises. This should not be new to us right now. This is kind of old news. Started talking about this on the first day of class. All right, high and low pressure areas. This is new to us now. When warm air rises, it does so in a counterclockwise motion. And it creates an area of low pressure below it because you have that air rising up. You have these gases rising up, so they're not exerting as much pressure down on the surface of the earth. And that's what we're talking about when we talk about air pressure. We're talking about how much pressure is that air actually putting down on the earth. So it might not seem like it because they're very light, but gases actually do have weight. And whenever the gases are cooler and they're descending down on the earth, they're putting more pressure down on the earth. When they're warmer and they're rising away from the earth, it's relieving pressure off the earth. All right, so now on the other hand, when cool air descends or sinks, it does so in a clockwise motion, and it creates an area of high pressure below. You can see that in the pictures. And you can go ahead and see already in the pictures that low pressure areas are associated with cloudy days and sometimes rainy weather. high pressure areas, they're associated with clear skies. All right, now let's talk about lateral movement of air masses. So we're talking about the movement of air masses across Earth's surface. Air masses move when they encounter a pressure difference with a surrounding air mass. Air flows from areas of high pressure to areas of low pressure. I always explain to students that this is like a balloon. All right, if you blow up a balloon and then you pinch the end of it off so the air can't escape, all right, and then you let go of the end where you've pinched it, what happens? And usually everybody says the air quickly escapes from the balloon. And the reason why that's happening is when you blew up the balloon, all right, you created a high pressure area inside the balloon as compared to all the air outside of the balloon. Okay, so the air in the balloon is under pressure, a higher amount of pressure, and it wants to escape to a lower pressure area, which would be the room that it's in. So it's kind of like that. Air wants to move from a high pressure area to a low pressure area. When air masses of different pressures meet, weather events occur. Okay, so let me reiterate something too. What causes differences in air pressure is the temperature for the most part. Okay, warm air is lower pressure. Areas of colder air is a higher pressure area. So when these low and high air pressure areas meet, or these warm air and cold air parcels meet, that's when we get our weather events: rain, snow, wind, storms, so on and so forth. All right, here you can see what we've been explaining. You have a high pressure area here where air is descending, cold air is descending, and here you have a low pressure area where warm air is ascending or rising, and air is going to want to move from that high pressure area into that low pressure area. And you can see here we've got what we've been talking about. You have warm air rising here and then cooler air descending here. You have a convection cell here. So here you have a convection cell. You would have the similar kind of convection cell over here. Same for over here. All right, now we can talk about weather fronts. So a front is a narrow region separating two air masses of different densities, pressures, and or temperatures. So basically it's just the boundary between two different parcels of air that have different densities, pressures, and temperatures. We have four different types. We have a cold front, warm front, stationary front, and occluded front. And actually, let's go over these symbols for them. All right, with a cold front, you have a line that has these triangular shapes on one side of it. And this indicates the direction of movement as well. The side that has the indicators on it shows you which direction that front is moving in as well. Now, keep in mind, here we have colors, but you should still be able to read these even when they're in black and white because of the difference of the symbols. All right, a warm front, the symbol is, a line with these semicircles. So even though we've got it colored red here, even if this was in black and white, you should be able to tell the difference between a cold front and a warm front due to the symbols. All right, a stationary front, it's almost like a half and half. It's like you got the cold front indicators on this side and the warm front indicators on that side. And then an occluded front, it's kind of the same thing, except all your symbols are on one side. All right, now let's talk about the characteristics of these fronts. All right, in a cold front, cold dense air displaces warm air and forces the warm air up. Now remember, the warm air wants to rise anyways, so when this cold air moves in on it, it forces it up even quicker. And the air that's getting forced up, it also cools off quicker than it would. So you can have kind of rapid cloud formation here. And these cold fronts are typically associated with cloudy days, rain showers, and thunderstorms. All right, in a warm front, you have a similar situation, but you have this warm air displacing cold air. And this is characterized by extensive cloudiness and precipitation. So this is cloudiness and precipitation over a large area. Okay, so you have the warm air moving in on this cold air, and it's kind of, this cold air won't sink anyways. It's kind of forcing it down, and then right here on the line where the warm and the cold air is meeting, you get, the development of clouds and precipitation. All right, in a stationary front, two air masses meet, and neither one really advances on the other. So you have cold air and warm air that meet, but they kind of just like butt up against each other and stop. It's as if they had an equal amount of force or something. It's like if you had two vehicles, that had come together and were pressing forward on each other, but neither one can cause the other to budge. Now, in a stationary front, some rain may occur, but rarely does it cause heavy precipitation. You usually have clouds, maybe light rain or misting, but rarely would a stationary front cause significant rainfall. All right, an occluded front occurs when a cold air mass moves so quickly that it overtakes a warm front. So really what you're getting is you got a warm front that has kind of tried to overtake this cold air right here, but then this other parcel of cold air ends up on this end of the warm front. And what happens is that warm front air gets forced up even quicker. So here you get, quick development of clouds. You get lots of precipitation. It's kind of like an exaggerated scenario of what happens during a normal cold front. All right, now we're moving on to cloud formation. Clouds form when warm, moist air rises, cools, and contracts. When the air cools to a certain temperature, now this temperature is not a set temperature. What temperature the air will need to cool to form a cloud just depends on the characteristics of that specific air mass. But when the air cools to a certain temperature, the water vapor is going to condense. It's going to go from being a vapor, from being a gas, it's going to start turning back into actual liquid water, and that's when you're going to get a cloud. All right, so here we can see we have the warm ground. We have air touching it. That air is warmed. It begins to rise, and then as it rises, it does cool, and when it cools enough, the water vapor in that cloud condenses. It starts to go back to a liquid from a gas, and clouds form. All right, now let's go a little more in depth on cloud formation. So a rising air mass will cool about 10 degrees Celsius for every 1,000 meters it increases in altitude. And this is the dry adiabatic lapse rate. So this is before the air mass condenses into a cloud. Okay, so that's down here. All right, as the air mass rises, for every 1,000 meters it rises, it will cool by about 10 degrees Celsius. All right, and then the air mass will eventually reach what's called its lifted condensation level. Now, at what elevation or what altitude that happens, it just depends on that specific air mass, how large it is, how much water vapor it contains, how warm it was or how cool it was from the start. Okay, but when it reaches that lifted condensation level, that's where the clouds form. Now, this isn't the end of that air mass rising. It will continue to rise after clouds form, all right? But then it slows, all right? For every 1,000 meters that air increases for every 1,000 meters that air parcel increases in altitude after the lifted condensation level or after cloud formation, it will only cool by 6 degrees. So if for every 1,000 meters it rises after the lifted condensation level, it only cools by 6 degrees. So you go from it cooling off by 10 degrees Celsius for every 1,000 meters, and then clouds form, and then it only cools by 6 degrees Celsius for every 1,000 meter climb in altitude or elevation. And that's what's called the moist adiabatic lapse rate. All right, and here we can see it again. This chart just demonstrates. See here, before clouds have formed here in the dry adiabatic lapse rate, all right, you have this air mass cooling by 10 degrees Celsius for every 1,000 meters that it rises in altitude. You can see that here, okay? All right, it's going up by 1,000 meters from the ground at 0 meters to 1,000 meters high. All right, this particular air mass went from 30 degrees Celsius down to 20 degrees Celsius. And then from 1,000 meters up to 2,000 meters, it decreased by another 10 degrees Celsius. And this just happened to be this particular air mass's lifted condensation level, 2,000 meters high. Now remember, that's not going to be the same for every air mass. It just depends on that particular air mass's characteristics. But for this one in the example, 2,000 meters proved to be its lifted condensation level. And now you can see after that, for every 1,000 meters it climbs, it only decreases in temperature by 6 degrees Celsius. So you see at about 3,000 meters, it has cooled to about 4 degrees Celsius. And then it continues to cool at that 6 degree Celsius for every 1,000 meters rate as it continues to go up. All right, the dew point is the temperature to which air must be cooled to reach saturation and form a cloud. Really, the dew point is basically the same, it's kind of the same term as lifted condensation level, more or less. In news weather broadcasts, you never hear them mention a lifted condensation level, but they're always talking about the dew point, you know. So the lifted condensation level is the altitude at which clouds form, and the dew point is the temperature that air mass will be at when it reaches its lifted condensation level. All right, now in the word saturation we've used before, and I've told you in science the word saturation typically means when something's full or holding as much as it can hold, and that's true for this as well. Saturation is the point at which that air mass is holding as much water vapor as it possibly can. All right, so on to humidity. Humidity is the amount of water vapor in an air mass. We have two types of humidity. We have absolute humidity and relative humidity. Absolute humidity is the maximum amount of water vapor an air mass can possibly hold. It's like a sponge. A sponge can soak up water, but a sponge can only hold so much water. Okay, you can't hold any more than its capacity. Absolute humidity increases when an air mass becomes less dense, and it decreases when an air mass becomes more dense. So in other words, an air mass, if it becomes warmer, its absolute humidity increases, meaning that it could take on more water than it could before. Because it is warmed, it is expanded and become less dense, so it has more room in there for water vapor to exist. Now, on the other hand, the absolute humidity of an air mass will decrease if that air mass gets cooler, because that air mass will contract, it'll become more dense, and there's less room in there for the water vapor to exist. Now, relative humidity is the amount of water vapor in a volume of air relative to how much water vapor that volume of air is capable of holding. It's kind of like if we had a bucket, and the bucket, say it could hold 10 gallons, and we had it half full. We'd say, okay, that bucket is 50% full. That's kind of what like relative humidity is. You know, if an air mass can hold a certain amount of water and it's halfway to that point, we would say the relative humidity for this air mass is 50%. Okay, so relative humidity can also change as absolute humidity changes. Okay, so let's say an air mass is at 50% relative humidity. It's holding half of the amount of water vapor it could be holding, and then it cools and the absolute humidity goes down, like its capacity to hold water vapor goes down. Right? The amount of water vapor in that air mass may not have changed, but if the air mass's capacity to hold water vapor is decreased, then it could go up. Like that figure, that relative humidity figure would go up. Maybe now we're at 75% relative humidity. Okay, because that air mass's ability to hold water vapor was decreased. Or say, we have an air mass and it's at 50% relative humidity, and it gets warmer and expands. Right, the relative humidity figure could go down. There's no water taken away. There's no water vapor taken away. But because the absolute humidity is larger, because that air mass can hold more moisture, the relative humidity figure has dropped. I know it's a little bit hard to think, but it's almost like thinking about, you're almost thinking of the air mass as like a bucket that can change size. You're not adding water or taking away water, but the bucket is changing size. So how full the bucket is or isn't, that's the figure that's changing. The relative humidity is changing with the absolute humidity. And by the way, if you're having trouble with that absolute humidity, relative humidity explanation, please send me an email, or I can give you a call or something like that, because that is a little difficult to understand. I can help with that. All right, precipitation. Precipitation occurs when a saturated air mass, an air mass that is holding all the water it can hold, it's at 100% relative humidity. If it continues to cool and its absolute humidity drops below the amount of water present in the air mass, that's when, precipitation falls down. Back to the sponge analogy I was using. Let's say we had a sponge and I put it under water and then I squeezed the sponge and then let go of it. That's what causes a sponge to fill up with water. All right, and then I pulled the sponge up out of the water, shook it off, and then I'm holding a sponge that's fully saturated with water. Okay? This sponge represents our cloud. All right? So if I squeeze the sponge, that's representative of what happens when an air mass cools and contracts and its absolute humidity decreases. All right? Our sponge was totally full of water. It's totally saturated, just as a cloud could be, totally saturated. It could be at 100% relative humidity. And then I've caused the absolute humidity to decrease. And so it's got to drop that excess water. Like the air mass's ability to hold water has been decreased. So that extra water, it just falls from the cloud. That's just like my sponge. If my sponge is totally full of water and then I contract the sponge, it has to drop the water that it can't hold anymore because the sponge has been contracted. And again, if that's kind of hard to understand from, just this verbal explanation, I can work with you on that. You just have to let me know that you need me for that.